Hello friends, in this lecture we shall study inner automorphism of a group and a result related to this inner automorphism. So I have written it as a lemma. This is our lemma number 20, and the lemma states that this is script I of G is isomorphic to G by Z, where script I of G is group of inner automorphisms of G and Z is center of G. We have not defined yet inner automorphism of a group. Now we will define inner automorphism in the proof of the lemma itself, and therefore the lemma is stated. Now we will define the inner automorphism and then we will define group of inner automorphisms. Now we consider the proof. We start the proof as taking G is a group. Let G be a group, and we take an element in G as small g, and G belongs to G. We define, consider a mapping, or we will write as consider a mapping Tg from G to G, defined by Tg of x is equal to G inverse xg for all x belongs to G. See, what we have considered, G is group, G is an element of G, and then we are considering a mapping function Tg from G to G itself, defined by Tg of x is equal to G inverse xg. So this is a conjugate of x by G, G inverse xg. Generally in abelian group it is trivial, because xg is equal to gx and this becomes equal to x. But in case of non-abelian group, so this is different from x. G inverse xg we have defined for all x belongs to G. Now we will show that this is automorphism. Now this is our claim. Tg is an automorphism. Automorphism of G. So this we shall prove. And after proving this, then we will define this as inner automorphism. First we have to prove the mapping defined by this is automorphism. And we know automorphism, we have discussed in last lecture. Automorphism is 1-1 onto homomorphism, or a 1-1 isomorphism of G onto itself. That is the set group we have considered, and first we shall prove it is onto. Tg is onto, and for that purpose we shall suppose let y belongs to G. Meaning of onto property, for every y belongs to G has inverse image x in G, then it will be onto. Let y belongs to G. Now we take x as x, we shall consider as say G. We will take the image x as G y G image, or take the element x as G y G inverse, and certainly this element belongs to G. Why? Because we have y in G, we have G in G, we written earlier G in G. So by closure property it is also in G. Now we will have the Tg of x. Now Tg of x is equal to, by definition of Tg, you see, it is G inverse xg, and that means it is G inverse xg first. And but what is the x we have taken as G inverse, x is Gy G inverse into G, and Now you see what will be this. G inverse G, Y, again G inverse G. So this is equal to G inverse of G, Y, G inverse G. And thus this is equal to Y. So Tg of x is equal to Y. This shows that Tg is onto. And thus Tg is onto. Now secondly, we may consider further as Tg is 1 1, or first we will show it is homomorphism. Second, Tg is homomorphism. Let xy belongs to G. We shall prove the multiplicative property of homomorphism, or structure preserving property of homomorphism. Tg of xy is equal to. Now what will be Tg of xy? Here we have xy belongs to G. See the definition of Tg. Tg of x is equal to G inverse xg, and therefore this will be G inverse. Place this element between G inverse and G. So it is G inverse xy G. And we want to show this is equal to Tg of x into Tg of y. And for that purpose, we can write this as G inverse x G, G inverse y G. Because of property of inverse, G into G inverse is identity, and thus the element is unchanged, G inverse x y G. And we now group these. And what is the first? First is, say by definition, G inverse x G is Tg of x. So this is equal to Tg of x, and this is Tg of y. By definition of Tg. This follows by definition of Tg. And thus we have shown Tg of x into y is equal to Tg of x into Tg of y, and thus Tg is homomorphism. So therefore we have proved it is a homomorphism. So I shall continue to write here. Therefore Tg is a homomorphism. What remains to prove for automorphism is 1-1 property. Three necessary properties for automorphism: onto homomorphism 1-1, or 1-1 onto homomorphism of G to itself. Third, Tg is 1-1. And let xy belongs to G. Now, what is a 1-1 property? We know. We will consider Tg image of x and y equal. So, Tg of x equal to Tg of y. What that must imply? X is equal to y. Then Tg becomes 1-1. So, by use the definition. So, definition Tg of x is equal to G inverse xg. So, this implies G inverse xg is equal to, and what is the Tg of y? Replace x by y. That is G inverse yg. And now we see this is easy to verify x is equal to y, because G inverse is prefactor and G is postfactor, and cancellation law holds in G. So therefore this implies x is equal to y by cancellation laws. And thus this shows that Tg is 1-1. Therefore Tg is 1-1, and we have shown Tg is 1-1, Tg is onto, and Tg is homomorphism. And thus Tg from G to G is an automorphism, or Tg is an automorphism of G. and this automorphism is called inner automorphism, which is called the inner automorphism. Inner automorphism of G corresponding to small g. See, we have taken the mapping Tg from G to G and it is defined by this Tg of x, G inverse xg, and we have shown it is 1-1 onto homomorphism and thus it becomes an automorphism, and this automorphism is known as inner automorphism of G corresponding to G. So thus we have defined now here inner automorphism. Inner automorphism is defined like this. And now further what we have to show, Ig is group of inner automorphisms. So this we have to consider the group of Ig is to be considered as inner automorphisms, all inner automorphism, and then we will show that it forms a group. But before that, if G is non-abelian, then it contains non-trivial automorphism that we shall mention here. If G is non-abelian, then there is a pair. There is AB belongs to G such that this product is not commutative. AB is not equal to BA. If it is equal, then it becomes abelian, and therefore we have say TB of A. So what will be a TB of A? That is equal to B inverse AB, and this is not equal to A. This will not be equal to A. When this will be equal to A, if AB is equal to BA, then B inverse B will be identity and then it will be A. So here AB is not equal to BA and therefore B inverse AB is not equal to A. And thus TB of A is not equal to A, then we have TB is not equal to identity. So that is TB is not equal to identity. A is I of A. A is equal to I of A. That means TB is not equal to I. And therefore, a non-trivial homomorphism exists for non-abelian group. So therefore, a non-abelian group G has a non-trivial automorphism. Non-trivial means which is not equal to identity. Identity mapping is always an automorphism, but there exists a non-trivial automorphism for non-abelian group. Now we define this script I of G as the group of automorphisms. So I shall keep this as it is. Now we define let I of G is equal to Tg, the inner automorphisms Tg such that G belongs to, or Tg belongs to automorphism. Tg is an automorphism, so this will belong to the group of automorphisms, and we have denoted the group of automorphisms by script A of G, and G belongs to G. See what we have done till now. We have shown Tg is inner automorphism, and now we are forming a set I of G, script I of G of all inner automorphisms. These are automorphisms we have shown. It is automorphism and called as inner automorphism, special automorphism, which is called inner automorphism of G corresponding to element G defined by this mapping. So we consider all such inner automorphisms and denote the set by script G and script I of G, and we now show this is a group or this is a subgroup of AG. Now we shall show this IG is a subgroup of A, script AG. Or this is our claim, IG is subgroup of AG. First is closure property. We have shown this is non-empty because it contains always the identity mapping as automorphism. So IG is non-empty. And the next property we shall consider as closure. For closure property, we shall consider two elements in IG. Let TG and TH belongs to IG. So what we shall form is the product of this, and again it must be in IG. Then it will be closed. So now we will have TGH of X is equal to, we will use the definition of T here, TG of X. Instead of TG we have TGH, and therefore this will be by this definition. So inverse of this GH inverse X into GH. See, the definition of TG of X is G inverse XG. Instead of G we have taken there GH, and further this is equal to GH inverse of GH by reversal law is H inverse G inverse X G H. Since we have inverse of AB is equal to B inverse into A inverse, and therefore inverse of GH is H inverse G inverse. Again we can write this as H inverse G inverse X G into H, and you see the middle element is here, that is TG of X. So therefore this will be H inverse TG of X into H, and again that H inverse TG of H will be TH. See, instead of G there is H, and therefore that will be TH. So this is TH of TG of X, and thus the left side we have is TGH of X is equal to TH TG of X, and thus hence we have TGH is equal to TH TG. So we will refer this as 1, we will use it again further, and this shows that TG and TH belongs to IG. This implies their product TH TG, which is TG or TGH, it is also in IG. So therefore TH TG belongs to IG implies TGH, their product is TGH. TGH also belongs to IG. Why this belongs to IG? Because GH belongs to G. TG, when we say TG is in IG, if G is in G, and GH is G and H both are elements of G, therefore GH belongs to G. Since GH is in G, and this shows that IG is closed. Their product is also that the product we have written the product like this, TH TG. The product is TGH, and that is also an automorphism, inner automorphism, and therefore IG is closed. Closure property we have proved. Now we shall consider existence of inverse. Second thing, let Tg belongs to Ig. If Tg belongs to Ig, by definition, see Tg is in Ig means G is in G. So this implies G belongs to G. And if G belongs to G, that will imply its inverse is also in G. G is a group. And if G inverse is in G, Tg inverse is in Ig. So this implies Tg inverse belongs to Ig. So by definition of Ig, Tg is automorphism. It's so this G inverse is in G, so therefore Tg inverse is in Ig, and thus inverse exists. Inverse exists for every element. In Ig, and thus this Ig is a subgroup of Ag, and therefore it is itself a group. Is a subgroup of Ag, script Ag, automorphisms. And therefore Ig is a group called a group of inner automorphisms. Inner automorphisms of G. So this is what we have stated in the lemma itself. Ig is the group of inner automorphisms, and thus we have defined and proved. We are doing both the things in the same proof. We are defining the terms and we are proving it, and we have proved it. It is group called group of inner automorphisms of G. Now once it becomes a group, now we shall consider another mapping psi from G to Ig. Now further, consider a mapping psi. Psi from G to Ig. This is a group. Just we have shown it is a group of inner automorphisms, and we now consider a mapping from G to group of inner automorphisms defined by psi of G is equal to Tg inverse for all G belongs to G. So this is our definition of psi. Psi is defined in terms of Tg inverse, because Tg inverse is in script I of G, just we have shown it because it is a group, and therefore we have defined this. Now what we shall prove is psi is onto homomorphism. We need onto homomorphism, and now we shall prove psi is onto homomorphism. Homomorphism with kernel Z. What is Z? Z is center of G, that we shall consider further. Now psi is onto homomorphism. First we shall prove it is onto. Psi is onto, and for that purpose we may consider say an element in this. Suppose Tg belongs to Ig. Let Tg belongs to Ig, and what we have to show, its inverse image exists, then it becomes onto. So if Tg belongs to G, G belongs to G. So this implies G belongs to G, and that implies G inverse belongs to G, and that implies Tg inverse will be in Ig. Now, what is the inverse image of this psi image of x, or we will consider psi of G. We have to consider G inverse is in G, so instead of this Tg inverse belongs to Ig, we will consider psi of G inverse. So what will be psi of G inverse by definition of psi? See, it is here. Psi of G inverse is equal to T G inverse, its inverse. Instead of G, we have here G inverse. So this will be T inverse of G inverse by definition. Replace G by G inverse on both sides. And what is the double inverse of G? It is Tg. And this shows that the inverse image of Tg is G inverse. And that means psi is onto. So this shows that psi is onto. Onto property we have proved taking Tg in Ig. Or you may consider Tg, if you consider Tg inverse in G, by definition of this itself, G will be the inverse image. And here we have considered Tg is in Ig, then its inverse image is under psi is G inverse. So this proves psi is onto. Now next is psi is homomorphism. Second, psi is a homomorphism. And to prove it is a homomorphism, let xy belongs to G. Two elements, xy belongs to G. And we will consider psi of xy. And multiplicative property, psi of xy, we will show it is psi of x into psi of y. So use the definition of psi. We are using the definitions of mapping each time. Earlier we have used this definition, now we are using psi. Psi of xy is defined by this. So this is T of xy inverse of xy. And that is equal to T of, so by reversal law this will be y inverse x inverse, and again this is so but we have to use the property of Tg also. So what is the Tg? Tg is G inverse xg, and therefore this will be, see, G inverse xy g. First we will use that property. T of inverse of xy. Using this, in place of G there is xy. So this is inverse of xy. So Tg inverse will be, say we want to use this one, and we should write inverse first. That is inverse of xy, again its inverse, and then we have to use for this as T of inverse xy, psi of xy we are to obtain, and then so instead using the definition, first we use the reversal law, and then we will see the definition. So first we can write this as T of y inverse x inverse, and now this is, so see our earlier equation we have written as TGH is equal to THTG. So this equation we have written, and by using this what will be this? This is first first th, that means this will be first tx inverse, and then it is a tg, means ty inverse. So by 1 this tgh is equal to thtg. Now you observe again. The elements can be used as gh or xy. We have written here xy. It may be written g into h. So psi of xy is equal to, by definition, t xy inverse of xy, and by reversal law it is y inverse x inverse, and by this equation, so it is a g and h. So this will be th first, means tx inverse and then ty inverse. But what is the tx inverse? By this definition, you see psi of x. This is psi of x. And what is the ty inverse? This will be psi of y. And thus we have shown psi of xy is equal to psi of x into psi of y. And this shows psi is a homomorphism. Now what remains to show is the kernel of psi, to find kernel of psi. Third, to find kernel of psi. Now let K be kernel of psi. Let capital K be the kernel of psi. By definition of kernel, what is the definition of kernel? So if an element is in the kernel, then its psi image must be identity. And identity of psi is mapping from G to Ig, means identity of this group. And identity of Ig is the identity mapping I. So therefore, G0, suppose G0 belongs to K, then this implies, and we write double implication, implies and implied by, psi of G0 is equal to identity of psi, and identity of psi is the identity mapping. That is identity of Ig. Identity of inner automorphism is the identity mapping. So I is identity of Ig. And thus this implies further, what is the implied and implied by, double implication we are writing. So what is the psi of G0? By this definition, it is T G0 inverse. T G0 inverse is equal to I, identity mapping. And now we consider the image of x under both mappings. These two mappings are equal, means Tg inverse of x must be equal to I of x. So this implies T G0 inverse of x is equal to I of x. And again, now we use on the left side, we use this definition of T. What is the Tg of x? That is G inverse x G. Instead of G, there it is a G0 inverse, and therefore this will be G0 inverse, double inverse of this first. So this is G0 inverse. You observe this Tg of x. Instead of G, there is G0 inverse. First is G inverse, means first is inverse of G0 inverse. X will be placed here, and then G. G means here G0 inverse. Applying the definition of, using definition of T on the left side. And what is I? I is the identity mapping, means I of x is equal to I. So this is by definition of T. I shall write the reason here, by definition of T. We have used this definition of T. T, not T, but Tg. Definition of Tg. And now you see this is actually G, G0. This implies and implied by G0 x G0 inverse is equal to x. Now we multiply both side by G0 and thus if you multiply by g naught, this becomes identity and this becomes x g naught. So this implies and implied by g naught x is equal to x g naught, and this is true for all x. So we should write here, this holds for all x belongs to g. So this is for all x belongs to g. X is in the group, and thus this also holds for all x belongs to g, and this is also holding for all x belongs to g. So g naught x is equal to x g naught for all x belongs to g, means this x commit with g naught, or g naught commits with every x. This implies, now I shall write here, this implies and implied by g naught commits with every x belongs to g, and this implies and implied by g naught is in the center of g. This belongs to g naught belongs to z is equal to center of g. See, because what is the definition of z? Center of g. Z contains those elements in g which commit with every element of g. Z belongs to g such that z is equal to zx for all x belongs to g. That is the definition of center of group, and we have proved it, defined and proved that the center of group is also a normal subgroup, and thus we have z is equal to center of g naught is in z. And now see the starting and the end of this these steps. We have started with g naught belongs to k, and we have obtained that g naught belongs to z. So that implies and implied by. That means every element in g naught in k is also in z, and conversely, means k must be equal to z, or k is subset of z and z is subset of k. So this implies, thus we have k is equal to z. But what is k? K is kernel of psi, and what is z? Z is center of g, and therefore the kernel of psi is z, and thus what we have, psi is onto homomorphism, we have proved, and its kernel is z. So hence psi is onto homomorphism. Is a homomorphism of g onto g by I, or we shall write like this. Psi is a homomorphism of g onto ig with kernel z. These we have proved earlier part. Homomorphism onto we have proved, and now we have proved kernel is z. And now here we apply the fundamental theorem of homomorphism of groups. And what the theorem says, fundamental theorem of homomorphism of groups. So if phi is a onto homomorphism from g to g bar, then the fundamental theorem of homomorphism says that this g bar and the with kernel k, then this g bar is isomorphic with g by k. This we have proved, theorem number 4. And we now apply the same theorem here. Psi is onto homomorphism from g to ig. So this ig must be isomorphic with g by its kernel. And what is the kernel of g? That is z. So that is ig must be isomorphic with g by z. Here the kernel we have denoted by k, and hence by the fundamental theorem of homomorphism of groups. This is theorem 4 we have proved. We have this Ig is isomorphic with G by its kernel. The kernel is Z. And this is what we wanted to prove. And this completes the so thus we have defined here inner automorphism. Then we have shown that Ig, script I of G, is forming the group of inner automorphism. And then we have defined, so this is a group that we have shown earlier, and then we have defined a mapping from G to Ig by this. And then we have shown that this is onto homomorphism. This is onto homomorphism and its kernel is Z. And therefore this group becomes isomorphic with G by its kernel, that is G by Z. So this completes the proof. Examples on automorphisms we shall have next lecture. Thank you.